Lesson 29, activities. Number 2 has to do with the snowball. Go ahead and read it before watching the video. So in this case, because the problem involves surface area, I feel like we're going to need the formula for the surface area of a sphere. But anyway, it does tell us in this case that the surface area is changing, decreasing at a rate of 1 square centimeter per minute. And because of the word decrease, we got to put a negative there. And we know the diameter is going to be 10 at some fixed moment in time, but I'm reluctant to write down that d equals 10 at this moment in time. We're going to hold off on that just so we don't fix this thing, make it static too early in the problem. So clearly, oh, and we didn't write the unknown yet. So it says we're looking for the rate at which the diameter decreases. So we want to find the d dt, the rate at which the diameter decreases. Okay, so clearly we need the formula for the surface area of a sphere. I suppose this is one that I would provide for you if you don't happen to know it, if I gave this kind of problem to you on a test or a quiz. So the surface area of a sphere is 4 pi r squared. And then we're going to take the derivative of both sides of that equation with respect to time. Derivative on the left is ds dt. 4 pi is a constant. Derivative of r squared is 2r, dr dt. Okay, so the fact is we don't have a dd dt in this equation, which is unfortunate because that's the thing that we're looking for. So I suppose there's one more thing that we should do, that we should come up with, is a relationship between d and r. And so the relationship clearly is that 2 times the radius is the diameter. And so couple of choices here. We could just take a derivative of both sides of this equation, and that would relate the d dt, which is the thing we want, to dr dt, which is the thing we have. But to be honest, I'm actually regretting taking a derivative of this equation because now I see that it gives me a dr dt, which is not what I want. So I think what I'd like to do instead, there's nothing wrong with this, but it isn't as helpful as I thought it was going to be. So now that I really think about it, I think I'd like to take this and use it to substitute and make it so we have only d's in this equation here. So that means we got to solve for r in this here. So r is equal to d over 2. And then we're going to substitute that into our s equation from up above. So it's 4 pi, and then instead of r squared, we're going to put d over 2. Okay, so let's square top and bottom. D squared over 4. 4's cancel, so we just get pi d squared. So I think this is going to be an easier equation for us to work with. I'll just write it again here. S is equal to pi d squared. Now we'll take a derivative of both sides of this equation with respect to time. ds dt equals pi. 2 comes down, I'll put it in the front, times d, subtract 1, and then times dd dt. And now you can see why I'm more happy than I was before, because dd dt is in fact the thing that we're trying to find. So now we're just going to plug in. We know ds dt is given up here as -1 equals 2 pi times d. Now d at this one moment in the problem is fixed at 10 centimeters. And so this is the moment to plug in that d equals 10, only after we've taken a derivative. You would not get anywhere if you plugged in d equals 10 here before taking your derivative. And then times the dd dt. And so just divide both sides by 20 pi. And I suppose units wouldn't be a bad thing. So the diameter here is changing at, what are the units for the diameter? Looks like centimeters, and then time is measured in minutes. Centimeters per minute. And you could type that on a calculator if you wanted a decimal. So you get around -0.0159 centimeters per minute. Okay, number 3. Again, pause the video and read this if you haven't done so yet. But I'm going to start with my diagram here. So we've got a person. That's stellar. And then we've got a light. Use your imagination on light. And then we've got this wall over here. And the light is shining. And the reason that we get a shadow on the wall is because the person is blocking some of the light. And so the person's shadow is only from here to here, because that's the part of the wall that is in the shadow because the person is in the way of the light. Okay, and so what is it? What do we have here? We got 12 meters between the wall and the light. And a person is 2 meters tall, so let's put that fixed at 2, there to there. And the person is walking from the spotlight towards the wall at a rate of 1.6 meters per second. So that feels like we should label this distance from here to here, because that is the thing that is getting smaller by 1.6 meters every second. So how about we call that one A? And then we can write that the rate of change of A with respect to time is 1.6 meters per second, except A is getting smaller, it's getting shorter, so we need to get a negative sign in there. So we're looking for the rate at which the person's shadow is changing. Okay, we're going to pause right there. That means that we need to symbolize the length of the person's shadow. So we're going to call it B. It's the length of that green vertical piece. And so it says find the rate at which the person's shadow is changing. So that means that dB dt is our question mark. And at some point, we're going to plug in that the person is 10 meters from the wall, and then separately, we're going to plug in 2 meters from the wall, but I'm not going to write either of those numbers here. We don't get to use either of those numbers until after we've come up with an equation and then written its derivative. Okay, so what are we going to do here? Well, I see 2 triangles. There is a small triangle over here, and then the bigger triangle here. And those 2 triangles are similar, so I'm feeling like we're going to use similar triangles here, which means that I need a label for the others for this bottom side of the smaller triangle. So let's go ahead and call that, and let's give that thing a name. We know the whole bottom line segment is 12, and the red part is A, so what's left over here must be 12 minus A, going here to here. And now I think I've got labels on all of the sides of my 2 triangles. So now I'm ready to write down my similar triangles proportion. So let's start with the 2. And the 2 is in the small triangle. And what's the corresponding side in the big triangle? That's labeled B, equals. And now because we started with the 2, that was a side of the small triangle, we must again start on top of this fraction with a small side, with a side of the small triangle. 12 minus A has to go up here. And then divided by the corresponding side in the big triangle, really common to put A here. It's also really wrong to put A there. What you need to put is the corresponding side of the big triangle, and that side is 12. A is only part of it. Just because it's labeled doesn't mean it goes directly in the proportion on its own. So here's our proportion. Okay, so I think we're good here. And what are we looking for again? dB dt. Okay, so you can mess around with this equation a little bit if you want. Like right now, we'd have to use quotient rule, right? If we could take a derivative of the left-hand side, I'll write it and then I'll erase it because I think we can avoid the quotient rule. But constant over x would become negative the constant over x squared, so it would be that. But then, of course, times the derivative of the stuff, right? So it would be fine to do that here. But if you cross multiply, then we can avoid the quotient rule entirely. So cross multiply, we get 24 equals B times 12 minus A. Okay, so I'm ready to take a derivative of the equation in this form. Left-hand side derivative is derivative of 24 is 0. Right-hand side, B and A are both variables. They're changing as time changes. So the derivative rule we need is the product rule. So we go first times, now what's the derivative of 12 minus A? Well, 12 becomes 0. Negative A, the derivative is negative 1. But then A is dependent on time, and so then the derivative of A is our chain rule. That's the derivative of the stuff. Plus the second times, and what's the derivative of the first? What's the derivative of B? So the derivative of B is just 1 dB dt. So that's our equation. And if we can just fill in like all of these numbers, all of these variable expressions, except for the one that we want, then we're good to go. So the one that we want is dB dt. So every other variable expression in this equation needs to become a number. So dA dt, looking right here, that's a piece of cake. That's negative 1.6. So the only other things we need to fill in are A and B. And now finally, we're going to come up here and it says when the person is 10 meters from the wall. So at that moment, A is equal to 10. So now we're ready to freeze this thing in time when A is equal to 10. But we also need to know what B is equal to because we still need to substitute for that B. And how are we going to calculate B when A is 10? Well, we've got this beautiful equation right here. Or if you prefer, this one right here. So we're going to plug in our A equals 10 into either of those equations. I'll use the second one. And that will allow us to find our B. 24 is equal to the B we're looking for times 12 minus, at this moment in time, A is 10. And so that's 2B on the right-hand side. So that means that 12 is equal to B. And that's enough information for me to plug in to my green equation. 0 equals, so we said B was 12. Negative dA dt. dA dt was itself negative 1.6, so that's going to become positive. Continuing with the green equation, plus 12 minus this A is 10 times dB dt. That's the unknown. I'll leave that right there. And then it's just arithmetic and a tiny bit of algebra. 0 equals 12 times 1.6. I feel like I should know that. Is that 1.92? 19.2, 19.2, how about that? Plus 2 dB dt. Just going to check my work there to make sure that we're good to go. Okay. And then subtract the, oh, we should have, this should not be 2b, this is just 2. And then subtract the 19.2 and divide by 2. And so we get dB dt, I'll put it over here, dB dt equals negative 19.2 divided by 2. All right, subtract and then divide. So is that 9.6, negative 9.6. Okay, and then the units there are the B units over the T units. So is it meters in seconds? Yeah, same as dA dt, meters per second. Okay, so at this one moment, when the person is 10 meters from the wall, the person's shadow is, the length of the shadow is changing by negative 9.6 meters per second. Does it make sense that it's negative? That would indicate a decrease of some sort. So remember, this person is walking towards the wall. And as the person walks towards the wall, what happens to the length of the shadow? Well, the person is going to be here, and then the person is going to be here. And you can see the length of the shadow indeed is going to get smaller. So the negative makes sense. Okay, and then one small change here. For the second part, the follow-up, when the person is 2 meters from the wall, so all we're doing is changing A to 2. So if we make A equal to 2, I think you'll see that B is equal to 10. I think that's right. Let's make sure. If A is 2, then this part right here becomes 10. Wait, did I do that wrong? A is 2, and B, I guess B isn't what I said it was. All right, so let's do the calculation here. So 24 equals B times 12 minus 2. So that's 10, so I guess that makes B equal to 2.4. And then everything else is the same. So we're doing the same green equation. I'll try to keep it on the screen there at the top. And so in this case, 0 equals, so instead of B now, we got 2.4, and then negative 1.6, and then plus 12 minus A, and now A is 2 times the dB dt. And then we just solve this thing for dB dt. So we're doing 2.4 times the 1.6, move that to the other side and divide by 10. And we'll do that in one fell swoop here. So 2.4 times the 1.6, and then it gets divided by 10, so it's going to be 0.384, but it'll be negative because we moved things over to the other side first. So dB dt equals negative 0.384 meters per second. And so you can see what that means as the person gets closer and closer to the wall, right? 10 meters from the wall versus only 2 meters from the wall. The shadow's length is changing rapidly in the beginning and then very slowly at the end. I actually do have a quick Mathematica player demonstration to show you. This is another free piece of software. It's called Wolfram's CDF Player. Bunch of free demonstrations up there that folks have made using Mathematica. You don't need to know anything about Mathematica. The programmers of demonstrations do, but not you. You can just take a look at their hard work. So here's the person. We'll just let this person walk towards the wall a couple of times. So first convince yourself that indeed the shadow is given by this thing right here. And then we're going to take a look at the rate at which the length of this shadow is changing. So it was supposed to be quick in the beginning and then slowly, slowly, slowly at the end. And then I think this distance right here is how far the person is from the wall. So if we put the person 10, no, actually I think it's backwards. So I think if the person, I think that is, I think that this is how far the person is from the light. So if we're 2 meters from the light, then it says the shadow is changing at negative 9.6. That's what we got because we were 10 meters from the wall. And then can I just type in 10? Maybe no. 10 there. And so then when the person is 10 meters from the light, they are 2 meters from the wall, and the shadow is changing at negative 0.384 meters per second. Okay, number 4 has to do with the boat being pulled into a dock. So if you haven't read the problem, read the problem. I'm going to start drawing. So we've got the water down here, and then we've got a boat. Like it's just so lifelike. And then over here we've got a dock, and the dock is 20 feet higher than the bottom here of the boat. So we're just going to pretend the boat is lower in the water than I have drawn. So we'll go ahead and draw this line right down to here. This is one of those funny boats where you pull it in by the bottom of the boat. And it says the rope is being pulled in at a rate of 2 feet per second. So that means that this should have a name, right? C, because then dc dt is 2 feet per second. Except the rope is being pulled in, which means the length of that green line segment is getting smaller. The length is decreasing, which means that dc dt is actually negative 2, not just 2. Okay, and then we're given information about, so it says how fast is the boat approaching the dock? So that tells me that I want to give a name to this length right here, because symbolically that's what they're asking us for the derivative of. So let's go ahead and call that one C. And then say that I said C, but I meant A. The ADT is the question mark. That's the speed with which the boat is approaching the dock, right? It's the rate at which the length of this blue line segment, pretend it's straight, is changing. And then we're given specific values of A. 30 feet out, we're given specific values of C. 30 feet out is C, and then 22 feet out is also C. Okay, so this feels like another Pythagorean theorem. Let's jump right in. A squared plus 20 squared equals C squared. Don't plug in any values of A or C right now. Take a derivative first. 2A, the ADT, plus the 20 squared is just a number, so its derivative is 0. 2C, the CDT. Divide both sides by 2 to make your life easier. And now we just need to find values of A and C, and then plug in the dCdt, which is that green negative 2 up there. Okay, so now we're ready to fix this thing 30 feet out. So let's do that here. When C equals 30, that's 30 feet out. How are we going to find the value of A? We've got the Pythagorean theorem right there. So when C is 30, A squared plus 20 squared equals 30 squared. So that means that A is the square root of 900 minus 400 is 500. And then we have enough to plug into our black equation right here. So A, square root of 500, we'll type it on the calculator in just a minute. The ADT is the unknown, equals C. C in this part is fixed at 30, and then dCdt was given up at the top here, -2. And so that means that the ADT is -60 over the square root of 500, which is approximately, and then some units, dA dt, so is this one meters per second, feet, and seconds, feet per second. So I'm going to type that on the calculator in a second, but let's do the other one just while we're here. So the other one is when there are 22 feet of rope out. So that means that C is 22. We get A squared plus 20 squared equals 22 squared. And so that means that A is, all right, so 22 squared is 484 minus 400 square root of 84. And so that means that our black equation changes now. I think we had, the start of it was A, so that's square root of 84 times the ADT, that's our unknown, equals C. So C in this part is 22, and then dCdt is always -2. So that means that the ADT is -44 over the square root of 84. And the nice thing about, well, the reason why I've asked you to find, like 2 different moments in time on the boat and 2 different moments in time on the spotlight shadow problem is so that we can see the rate at which we can compare the rates of change, right? Is it slow then fast? Is it fast then slow? Or are the rates of change constant? Okay, so we're just typing these things on our calculator here. So -60 divided by the square root of 500. That's our first answer. And then -44 divided by the square root of 84. That's our second answer. So -2.68 and 4.80. Feet per second for both of them. Why is it negative? Well, I guess probably we should have made it positive really at the end here because it says, well, it says how fast. I guess that's a synonym for speed. So why were the dAdt's negative? What's happening to the length of this line segment as the boat is getting pulled in? It's getting shorter. So the length of the line segment is decreasing. So the negative makes sense, but I guess if we're just asking for speed, then you would say that the speeds are positive, right? Positive 2.68 feet and then positive 4.8 feet. And you can see that when the boat is 30 feet out, it is getting pulled in this way, not as fast as when the boat is only 22 feet out. So apparently it's racing towards the dock faster and faster as it gets closer. Okay, number 5 is a doozy of a problem. Go ahead and read it. I'm going to start with my picture here. So we've got our clock, and we've got like some generic moment in time with an hour hand and a minute. Sorry, that's the minute hand first, and then the hour hand is the shorter one. And it says the hour hand's length is 2. Do not put a variable there. The minute hand's length is 4. And then we're interested in how fast the distance between the tip of the minute hand and the tip of the hour hand is changing. So it sure feels like we need to mark that distance. Let's call it C. And then at 1 o'clock is a fixed moment in time, but I'm specifically not at 1 o'clock right now. I'm at like a general moment in time. Okay, so how are we going to get our hands on an equation? Oh, and so dCdt is what we're after, right? dCdt is the unknown. So how are we going to get our hands on an equation for this one? Well, the twist here is to actually, so we can't use Pythagorean theorem because even though this triangle looks like it might be a right triangle, in general, it's not a right triangle. So can't use Pythagorean theorem, but you're going to use something that generalizes the Pythagorean theorem. And that thing we're going to use is called the Law of Cosines. So if that's enough of a hint, you might pause the video here and see what you can do before coming back to check out the rest. But if you're still with me and you want to see more details, here they are. The law of cosines says c squared equals a squared plus b squared minus 2ab cosine of the angle in between them. I'm going to call that capital C here, but that angle is actually theta in our picture. So in this case, specifically, it's c squared equals 4 squared plus 2 squared minus 2 times 4 times 2 times cosine of theta. And we're going to do some arithmetic to clean this up. C squared equals 16 and 4 is 20, minus 2 times 4 times 2 is 16 cosine of theta. So that right there is an equation that relates C, the thing we want, to theta, the thing that I'm really not sure why it's labeled, other than the fact that I've done this problem before. But anyway, we've got an equation, and let's go ahead and take a derivative of it. Time, again, is the underlying variable. So 2c dc dt equals 20 minus, 20 disappears, minus 16 gets copied. Derivative of cosine is negative sign, so that changes us to a positive because of the negative in front of the 16. So it becomes 16 sine of theta, but then times d theta dt. Okay, so where are we right now? Well, we're looking for dc dt. So let's highlight that one. This is the only thing in this equation that I don't need to substitute for. So what that means in order to solve for dc dt is that we need to know a specific value of c and a specific value of theta and a specific value of d theta dt. Okay, let's begin with the specific value of theta. At this one moment in time that we're interested in, it's 1 o'clock. And if you think very carefully, you should actually be able to figure out exactly the value of theta when you are at 1 o'clock. Because when you are at 1 o'clock, you know that the hour hand points to the 1, and the minute hand points straight up to the 12. And that theta angle in between there is fixed. It's calculable, right? I mean, like we know that the whole one complete revolution is 2 pi radians. And what fraction of that 2 pi radians is this? Well, it's a 12th of it, right? 12 hours on our clock. So the specific theta that we want is 2 pi divided by 12. So at 1 o'clock, theta is equal to 2 pi cut into 12 equal pieces, or simply pi over 6. Great. So that's one of the unknowns that we were after. We now know this one. How are we going to figure out what c is? Well, at this specific moment in time, if I know exactly what theta is, pi over 6, then I can use this equation right here. I can plug in a pi over 6 right there for theta, and then I've got enough information to find c. So let's use that. So this equation is coming right here now. C squared c squared equals 20 minus 16 cosine of theta, which is now pi over 6. Okay, so this becomes c squared equals 20 minus 16. Okay, so cosine of pi over 6, that one is root 3 over 2. And so c squared is equal to, so 20 minus the 16 and the 2 can reduce to an 8 over 1. So 20 minus 8 root 3, and therefore c is the square root of 20 minus 8 root 3. Okay, so I just typed that onto the calculator to get a decimal. I'm going to store this as c because I think we're going to use it later on. So about 2.48. Okay, so let's regroup and come back to the derivative equation. Where'd it go? This black one here in the middle with the highlighted dc dt. So we just calculated a value of c. It was around 2.5. The theta we said was pi over 6. So the only thing that we need in this one, we need still to calculate is d theta dt. So it sure feels like we're fresh out of information, right? Like we've used everything in this particular problem. We've used all the givens. There's nothing special about 1 o'clock, I don't think, to help us find d theta dt. We've used the law of cosines equation. We calculated a specific theta up here, and then we used the cosines equation to get the specific c. So what's the twist here to find d theta dt? Well, the fact is d theta dt on a clock is actually always a specific fixed number, and it might not be something you've ever thought about, but it is something we can calculate. And so it's sort of independent of everything else we've done in this problem. So the reason that this angle theta here changes, well, there's two reasons that it would change. One, the hour hand, as time passes, moves a little bit this way, and the minute hand moves a lot, like faster than the hour hand that way, right? And so there's two things that are changing, both of which have an impact on the way that theta is changing. So would you agree that the rate at which theta is changing is the rate that the hour hand moves minus the rate that the minute hand moves? I'm going to write that right down here. So this is a general clock fact. D theta dt is equal to the rate that the hour hand rotates minus the rate the minute hand rotates. And the rate the hour hand rotates, well, let's just think about how long it takes for that hour hand to go completely around one complete revolution. I know there's 2 pi radians. And how long does it take for the hour hand to rotate around 2 pi radians? It takes 12 hours for that to happen. So that is the rate the hour hand rotates minus. And now the minute hand, again, thinking about one complete revolution for just the minute hand. Again, it's 2 pi radians for that revolution. And how long does the minute hand take? It takes 60 minutes, but let's be consistent with our time units and say that it takes 1 hour. So those are the rates that these two hands rotate independently of each other. And we simply subtract those rates, and that will give us an exact measure for the rate at which theta is changing. And even the units make sense, right? We know that the units for d theta dt will be radians per hour. And that's exactly what the units are for these two fractions. Okay, so let's just combine here. That's a pi over 6 minus a 2 pi, which is pi over 6 minus 12 pi over 6, or negative 11 pi over 6. That is the rate that the angle is changing. Rate the angle is changing between the hour hand and the minute hand. So why is it negative? Well, it's just negative because of the order in which I subtracted my two rates. I said hour hand first and minute hand second. If I'm thinking about 1 o'clock, which is pretty close to the time that I've drawn here, or I guess you could say over here, 1 o'clock, is this theta increasing or decreasing? Is it getting bigger or smaller as an angle? And so at 1 o'clock, it's getting smaller. So I like the fact that I've got a negative down there in my answer. But if you waited until, say, for example, 1:15, so it'd be like the hour hand there and then the minute hand there, then the theta now is getting bigger, and d theta dt would be positive. So you just have to subtract in the right order. But I think that at any moment in time, that angle is changing at negative 11 pi, or at 11 pi over 6 radians per hour, sometimes positive, sometimes negative, depending on the relationship between the hour hand and the minute hand at the moment in time you're looking at the clock. Okay, so I think we've got all the pieces we need. So coming back up here to this starred equation, the one in black, we're just going to rewrite all of that stuff. Don't quite have enough room to see, maybe we can do it in the bottom right here, a little bit of space down here. So here's the starred equation coming down. So 2c, c we calculated in green, it's roughly this 2.48 equals 16 sine of theta. Theta was, where was theta? It's pi over 6. And then times the d theta dt. We just, am I missing something? I am. So on the left-hand side, I forgot my dc dt, which is kind of a problem because that's the whole point of this question. So 2 times c times d theta dc dt. Okay, we got it now. Right-hand side, I just need my d theta dt, which we just calculated was a negative 11 pi over 6. And I think we're good to go. Now it's just arithmetic and a tiny bit of algebra. Okay, so 2 times the 2.48 number, dc dt. Just have to evaluate this sine of pi over 6. That's a half. 16 times a half times negative 11 pi over 6. Now I'm ready to go to my calculator. I mean, clearly you can reduce over here, but ultimately I'm just going to get a decimal anyway, so that's what I'm doing right now. Okay, so don't forget C, we've still got here, that's that 2.48 number. Okay, so we're doing 16 times a half, that's 8, multiplied by the negative 11 pi over 6, divided by the 6. Nope, sorry, that's already divided by 6. And then we're going to divide by 2 times this 2.48 number, the whole thing divided by 2.48. So take that divided by parentheses around 2 times 2.48, but I'll just call that alpha C. Now I've got our answer, negative 9.29, almost 9.3. Okay. And the CDT is measured in C units over T units, which is inches per hour. So the distance between the tip of the minute hand and the tip of the hour hand is changing by 9.29 inches per hour. At 1 o'clock, it is decreasing because those 2 points are getting closer to each other as the hour hand, as the minute hand catches up to the hour hand right around 1 o'clock. It's not going to, I mean, 9.29 inches per hour might feel like a large number, but the fact is, we're only looking at this one particular moment in time, and I guess when these two hands are near each other, the 2 points are getting close to each other pretty quickly. So we're not saying, like that rate is going to stay the same. It'd be interesting to kind of calculate at different moments in time, at 2 o'clock, at 3 o'clock, at 7:45. How does this number change?